Okay, let's take a closer look at our first case, which is real and distinct poles. So we have a generalized function here, f of s. We have some numerator polynomial, which we're not really worried about, other than to say that we assume we have a proper rational function. So we have a proper rational function, but other than that, we don't really worry about at the moment for of what our numerator function is. We'll see an example of how we deal with that. And we have all of these poles in the denominator. We have s plus p1 times s plus p2, so on and so forth, times s plus pn. So the one qualifier we want to give to this is we want to say that p sub I is not equal to p sub j for all I not equal to j. And so all that is saying is that's just a fancy mathematical way of saying that we have distinct poles. So none of these two poles in the denominator are the same. So if that's the case, we know that we can rewrite this as f of s equals k1 over s plus p1 plus k2 over s plus p2 plus dot dot dot, so on and so forth, all the way until we get to that last one, which is going to be k sub n over s plus pn. So now what we're going to do is we want to find these coefficient terms. So we want to find k1, k2, all the way up to kn. So k1, k2, dot, 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 all the way to kn. The technical name for these is residues. So these coefficients in our time domain are called residues of f of s. And so what we're going to look at here is something called the residue method. And so there are other methods which I'll mention later on, an algebraic method, but personally I find this residue method to be a lot easier. So what our residue method is considering this equation up here, what we're going to do is we're going to multiply both sides by s plus p1. So let's say multiply both sides of that equation above by the quantity of s plus p1. So what we have then is on our left side, we're going to have s plus p1 times f of s, and our f of s is just going to be this general function here. And so again, this will all be clear once we look at a numerical example in the next video. And on the right side, we're multiplying s plus p1 times each of these terms. So we can see for this first term, our s plus p1 is going to cancel out, and we're going to just be left with k1. Now, because we said our poles are distinct, none of the other ones are going to cancel out. So we're going to have s plus p1 times k2 divided by s plus p2. And that's going to be true for all of our other terms, all the way up to s plus p1 times kn divided by s plus pn. And so what we want to do now is we want to evaluate at s equals negative p1. So evaluate at s equals negative p1. And so why would we want to do that? Well, what we can see is every term up here that still has an s plus p1 is going to go to 0. So all of these terms, when we evaluate at s equals negative p1, are going to go to 0, and we're going to be left with just this k1 on the right side. So now we're not worried about this term over here going to 0, because if we come back up here, remember our f of s is this function here, so we're going to be canceling out with our s plus p1 here, but so we're not going to be going to 0. So the way we can write this mathematically is we can say s plus p1 times f of s evaluated at s equals negative p1. So that's how we would write that mathematically. And based on our argument up here, we know that all of these terms are going to 0 except for k1. So we can say that's how we can solve for that residue k1. So we can take this a step further and we can generalize this to if we want to solve for some coefficient k sub I. So our coefficient k sub I is going to be equal to s plus p sub I, where pi is the pole that corresponds to that coefficient, times our f of s, evaluated at a value of s equals negative pi. So this would be an important equation in order to help us more easily get our coefficients. We could also generalize our resulting function in the time domain then. So in this case, we just have all of these simple poles, s plus p2, and of course we can, if we have something more complex, we can factor it out and we can get something that is simple. And so we can say in general then our function in time, f of t, is going to be equal to, and so we're going to have all of these terms which ultimately are going to be multiplied by our unit step, but we have k1 e to the minus p1t plus k2 e to the minus p2t plus so on and so forth all the way until we get to k sub n e to the minus pnt. And all of that is multiplied by u of t. And so again, all we're doing there is just using our operational and functional transforms, which we can find in a table of Laplace transforms, to go from this equation up here to our time domain f of t. So what we're going to do in the next video is we're going to come back and we're going to look at an explicit numerical example and see how we can use this equation to help us find our residues.